This is our last video on the subject of stacks. This video summarizes the stack operations that we've seen and compares and contrasts the list-based stack and the vector-based stack. So remember, the major stack operations are top. You can get the top element of a stack, push to add a new element at the top, and pop to remove the top element. We've seen a linked list-based stack that uses a singly linked list to implement those operations, and we've also seen a vector-based stack that uses a vector to implement those operations. They're both kind of the same in that they are container adapters. The linked list-based stack just implements all of these operations, top, push, and pop, by calling into linked list operations that do all of the real work. And similarly, the vector-based stack is an adapter that implements top, push, and pop just using vector operations. There is one important difference, which is that for performance reasons, the linked list stores the top of the stack at the front, and the vector-based stack stores the top of the stack at the end. Here's a comparison of the asymptotic efficiency, or big O, of the two of them. So our operations are default constructor that creates an empty one, and for the list-based stack on the left and the vector-based stack on the right, it's constant time. The size operation is constant for both of them, big O of 1. Getting the top is constant for both of them. Pushing is constant worst case time for the list-based stack and constant amortized time for the vector-based stack. And popping is constant worst case time for the list-based stack and constant amortized time for the vector-based stack. So what you can see when you summarize all this together is that all of these operations are efficient. They're constant time in every case. So this is a very fast data structure, whether it's list-based or vector-based. And the only difference we can pick out on this chart is that the mutation operations that change the stack, meaning the push and pop, are constant amortized time in the case of the vector-based stack, but they're just plain constant time in the case of the list-based stack. And the reason for that difference is because of how vectors do their resizing, where occasionally a new array has to be reallocated. And that occasional slowdown from the occasional resizing makes these constant amortized time bounds, because occasionally they're slower than constant time. So the takeaway, both are efficient, the list-based stack and the vector-based stack. You can't go wrong using either one of them. They all have constant time, top, push, and pop operations. The vector-based mutation operations, push and pop, are constant amortized time due to the resizing, which maybe could be a negative in some cases. However, remember back when we were comparing singly linked lists, doubly linked lists, and vectors, we saw that the singly linked list had worst constant factors, meaning the vector is more space efficient because it stores all of its elements in a contiguous array that only wastes up to 50% of the space, whereas the singly linked list wraps every element in its own node. So every element has at least one extra word of overhead due to the node pointers. So the vector is a little more space efficient. It uses a little less memory. And the vector is faster. My experiment in that earlier video showed the vector is 3 or 4 times faster than a singly linked list. It gets the same number of add operations done 3 to 4 times faster in a third of the time. So that says kind of for your general purpose stack, if general purpose software development, the vector-based one is probably the one to go with because they are comparable in terms of their asymptotic efficiency. It's constant either way, but you would expect the vector to be about 3 or 4 times faster, and there's no significant downside, so you might as well use the vector. However, if those amortized operations are unacceptable because you absolutely need consistent time per operation, then the list-based stack is the one to go to. So some software applications can't abide having these occasional resizes that are slower every once in a while, and those are the situations where we would choose a linked list-based stack. Here's the final summary, once again, of all of these operations just for your reference, and that's it for stacks.